This should be the last one. I didn't hear the chirp last time, so I kept going afterwards, and I was like, oh crap. So, what I was just saying, the problem tells us big M is equal to 3 times little m. What's the acceleration of the supplies on their way up? Here are my free body diagrams from before. Here are my net force equations for little m. Tension minus the force of gravity on little m equals MAY. I bring that down to here. Big M, force of gravity on big M, minus tension equals big M, AY. I substitute 3m in for big M, I rearrange, I bring this equation in, I solve for tension. I'm hoping that you guys, and I know I'm skipping ahead here, so maybe take a second, pause, write this down. I'm fairly confident you guys know how to do this. We end up with the acceleration of the system is equal to g over 2, acceleration due to gravity divided by 2. What that means is the big mass falls at a rate of, the acceleration is half that due to gravity. That means the little mass supplies go upwards at the same acceleration, okay? Now, this is ideal. This is without mentioning anything whatsoever about the pulley. In real life, however, if you take a second to read the back, the acceleration is lower than expected. And the workers want to know why. Why is the acceleration not quite as big as expected? You are to answer. They figured out eventually it's because they didn't take the pulley into account. You are to answer in, and this is the phrasing the AP uses, a clear, coherent paragraph length response why this is. Why is the pulley important? The property of the pulley that is important here, that we did not take into account, you can't just say the mass of the pulley, you have to say the rotational inertia of the pulley. So here's how I said it. The pulley likely has some rotational inertia. And what that means, meaning it takes a non-zero force to cause rotation. This contributes, if I could spell that would be great. I'm trying to finish this up in this video, so I'm trying to go fast here. This contributes to the overall inertia of the system which makes it, I guess I'll say, harder, in quotes, to move the system. This is kind of like if we were just talking about something moving linearly, dumping more mass onto it, okay? Putting more mass on the object. It's harder to make it move, harder to make it accelerate. If you put the same forces on there, it will accelerate less. So we've made it harder to move the system. So, with the same forces, the acceleration must be smaller, just as the workers found. Seems like it makes sense. We didn't take into account the pulley has some rotational inertia. Now, the fun part for me, and maybe for you, I don't know. The fun part now is us trying to figure out, okay, well, what is the actual, predicted new acceleration? What is the new acceleration of this pulley? We are told the mass of the pulley is also 3m, and it has a radius of big R. We are asked to calculate the actual acceleration of the supplies, okay? That would be a linear acceleration. Supplies are accelerating in a straight line, not an angular acceleration, a linear acceleration. So, we know from before, the rotational inertia of a disk is 1/2 m r squared, okay? Which, in this case, I guess we could say, since we know that the mass of the disk is 3m, 1/2 3m r squared. This turned into, I guess, 3/2 little m big R squared. And again, remember, the rotational inertia of any object that you need, other than a point object, will always be given to you. Let's get our free body diagrams back. Okay, let's at least draw those. This is little m, Fg, little m. Now remember, the tension on this pulley, now you're going to have two different tensions in different sides of the string. Okay, otherwise the pulley wouldn't rotate. I'm going to call this one Tm. That's the tension on the side that has little m. So I'm going to call this one, this tension, T big M. Now, if you're with me from the last time, hopefully you realize that if M, big M is descending, little m is going up, that means our pulley must be rotating clockwise. Okay? So clockwise is going to be positive. And that also means that we should get T big M is bigger than T little m. I don't know if we actually go and find that in this case, but they will be different. Here are the forces on my pulley. Obviously my pulley is suspended by something. Okay, obviously it has some mass. We know the mass acts from the center of gravity. That is not going to cause any torque. It's probably held up at the axis at the center of gravity. Okay, that is also not going to cause any torque. We'll just call it normal force. The only torques are going to be the tension on each side. T capital M, T lowercase m. What we need now is we need net force equations for each of these. Just going to separate them. For little m, okay, and this is mainly the same thing that we were doing before. F net y equals T little m minus Fg little m equals little m ay. That would be T little m minus Mg equals m ay. T little m equals Mg plus may. Over here, oh geez, I really did not give myself a lot of room for this. F net y equals Fg big M minus T big M equals big M ay. That would be Mg minus T big M equals big M ay. I know this is really 3Mg minus T big M equals 3M ay. T big M equals 3Mg minus 3M ay. Okay? Pretty much the same as last time, other than I just threw the m's in. The torques, okay? We don't need net forces here, okay? It's not translating. It is not, however, in rotational equilibrium. So we need to write out our net torque equation. T net equals, the torque that's positive is the torque from the big mass, T cap torque, or tau capital M, minus this torque, tau lowercase m, always equal to I alpha. The equation for any torque is R times the force itself times sine theta, and I'm putting subscripts so I know exactly which ones I'm talking about here. This is Rm T lowercase m sine m theta m. Rotational inertia. We already found out, we did at the top, that it was 3/2 little m capital R squared. By the way, maybe I'll add to my diagram. These are both capital R, it's the radius of my pulley. And, wait a sec, alpha, I know that alpha is equal to A times R. And in this case, A is AY, R is this capital R thing, okay? The linear acceleration, we're talking about the linear acceleration in the y direction, times the radius. Now we play our game again. I can cancel out the R's here. Cancel, cancel. Rm, the distance that this force acts from the center of rotation is capital R. T big M is 3 little mg minus 3 little m ay. Force R, they're perpendicular. Matter of fact, so is the other one. I'll cancel those out right now. So this does not play any role. This is also r. The distance that this force x from the center of a rotation, from the axis of rotation, is little r. T little m is mg plus may equals 3/2 m r ay. We are looking for ay. We don't want to cancel that out. That would be bad. However, I do have an r, an r, an r. Cancel, cancel, cancel in every single term. I also have an m in every single term. I cancel the m's. Look at all this stuff that cancels. I'm left with this. 3g minus 3ay minus g minus ay. Please remember to distribute the negative. Equals 3/2 ay. I'm looking for ay. I need to get all these terms over here. I'm going to end up with 2g over here. And then over here, I'm going to turn everything so I can add these a little easier into fractions. So this is add over 2 over 2ay plus 6 over 2ay. Let's see, common denominator, great. 3 plus 2 plus 6 is 11. So I get 2g equals 11/2 ay. I solve for ay. I end up with an acceleration of 2 times 2 is 4 over 11. 4/11 times the acceleration due to gravity. Now, how we said initially that if we don't take the rotational inertia into account, we get g over 2. Okay? This is smaller than g over 2, just like what we predicted. We see that it's smaller. Okay? This is in line with what we predicted and what they observed. If we take the rotational inertia of this into account because it has mass, it means it's something else to move. It's harder for those forces to cause this whole system to move. They do not accelerate at as great a rate. Okay? Hopefully you see here, it's a very similar process to when you did the first example. It's very, very similar. It's almost, it's different numbers obviously, but it's the same process. As you do this more and more, the process gets easier and easier. Okay? Study that. That is the main thing I want you to understand from this, is just knowing it's not that much harder. We just have to integrate we have to do a net torque equation now, if we're dealing with a pulley that has some rotational inertia. Last question, and then I promise I will shut up, go home for the night, get some sleep, come back tomorrow morning, and do the same thing. Let me just give a check on our time so we know what we're working with. Okay, about 5 minutes. Even though this acceleration is smaller, it would not necessarily make this system easy to work with. This is just kind of like my common sense question I like to throw in there every once in a while. Why might a constant acceleration all the way up to the top not be a good idea? How could the workers modify their system, make it better? Well, we said there's a constant acceleration, 4/11 g. That's actually still a pretty fast acceleration. That's like tilting a ramp up to like this and letting a cart go down. That cart accelerates at a pretty quick rate. Imagine trying to stop the supplies at the top. If that acceleration maintains all the way to the top, they're hauling by the time they get up there. It's moving really, really fast. So this might not be a good idea, because there is the question of how will you stop it? How will you stop the system? How will you stop either the supplies getting to the top where you need them, or the giant mass crashing down to the ground? How are you going to stop the system when it reaches its desired position safely? Okay? Your construction crew, you want to make sure no one loses a finger, or worse. All right? How will you stop the system safely? So, a couple things I might consider. I suppose what you could do, somehow use some springs. You could attach springs to serve as some, I don't really, again, I'm a terrible engineer, okay? This is why I'm a physics teacher and not an engineer, because I do not have any sort of building intuition whatsoever. All you people who turn into engineers, in 5 years, 10 years, you can come back and laugh at me and be like, you don't know what you're talking about, okay, in terms of like real world stuff. I know the principles really well, but this, I'm not an engineer for a very good reason. I have very little building intuition. Much better at coming up with and solving problems. Not that you don't have to do that as an engineer, but I'm I'm good at what I do. I'll leave it at that. You could use some springs to serve as a brake, or use some sort of other mechanism. Some other mechanism. To slow system down before it reaches its desired position. You guys know me, I like to tie in the kind of common sense stuff back to the problems that we go through. I try to make them real world. Okay? I try. I think really hard about a lot of these. What I'm really interested in you guys getting from this is the idea that if you have an object that is moving, okay, some sort of system that is moving and rotating, you do have to take into account the rotational inertia of the parts that are rotating. It's not really that you have to do anything really hard or really complex, they just need to be added into what you're doing, okay? You need to add those equations for the net torque in to find the full picture of what's going on, okay? Because if something has rotational inertia, you need to account for that when you're accounting for all the different forces and torques, all right? So just remember, take the two-body problem that we're used to solving, that we started solving back in October, and now we're adding to that. If there is an object that is rotating, like a pulley, something has rotational inertia, we need to account for that. It's not particularly hard. I would try a bunch of those problems, okay? See where you get to with them, okay? Obviously come ask me for help if you need to. And that's it for this. You have some homework that you can work on. I'm obviously more than happy to answer questions for you in person once we get back, or on email, I guess, that's fine too. And their next topic, which I will be doing some videos for tomorrow morning, is rolling, okay? Objects that roll. That's another favorite topic of mine. It's very interesting. So I will see you, well, I guess on Tuesday, but you will be seeing me not on this video anymore. Bye.